So before I start, let me just mention one thing related to the last question that we had. Just because I want to be a little bit more precise about this whole issue of what exactly is one showing, and let me actually highlight also some very interesting and quite recent counterexamples that have to do with the following. So imagine that we have, as I said before, we were just talking about the decision question, right? I have a polynomial, and I want to decide whether it's a sum of squares or not, and this is exactly reducible to this kind of nice semi-definite programming question. But there's some things that can be a little bit tricky. And there's in particular some examples, some very nice examples due to Scheidler, where you can have a polynomial with rational coefficients, right? And I'm trying to find or decide whether this polynomial is a sum of squares or not. The geometric picture, as I said, is really trying to decide the feasibility of this semi-definite problem. So I'm really trying to find the intersection of this subspace L with the cone of positive semi-definite matrices. And much of the difficulty is that, or one of the funny things that can happen, is that I may have my subspace barely touch my cone at a single point. And even worse, what can happen, like in this nice example, is that even if P is rational, rational coefficients, then the only Q for which this is true is that Q is irrational. Right? So somehow, if you want to ask any kind of questions about bit representation, then the question is, okay, how are you even going to represent Q? What does it actually mean?
Is it algebraic?
Yes, it's algebraic.
So it's not too bad.
Yeah, it's not a bad thing, but I think one has to be, again, careful about it. What typically one does, because again, you don't want to deal with this question directly, is that instead you look at the approximate question. And there's kind of a couple of different ways of looking at it. Either you think about whenever I put an epsilon in there, then what can I say about finding a Q? Because really zeros of this polynomial are very problematic. And this is something that it's not specific to sum of squares. There's a lot of other approaches based on discretization or linear programming relaxations and all of stuff. And it's quite typical that the running time will depend actually on on the value on 1 over the minimum of the polynomial, or some function that really has to do with how close a minimum of the polynomial in the unit sphere or in the unit circle or whatever it happens to be. So again, if you really, the only point is if you want to be really precise about it, then somehow one should care about the approximate complexity question. And in that case, somehow things are nicely behaved in terms of what this epsilon is. But the point is, really, we cannot expect at least at the naive representation of of Q will work, because again, there are certainly examples when Q doesn't need to be rational.
What would be the dependency on the bit complexity of epsilon?
I don't remember, but essentially, I think certainly even the ones that come from linear programming, this is I think particularly nice. I don't remember. I can give you some references. By the way, the other thing that I should mention, is that this is exactly somehow whenever this happens, it's exactly because things are very close to being infeasible, right? If you think in terms of condition number or something like this, that's exactly a situation where things, a polynomial having zeros, my situation where the subspace is barely touching the cone, is exactly a situation where small perturbations will actually change the answer of the problem. So somehow it is very natural always of problems of this type that you really want to think in terms of condition number, right?
So there's no polynomial bound on the size of the QI in terms of P, right?
Size of the QI?
The number of coefficients which are non-zero and so on. It can be much more than any polynomial. N to the D is a bound one can get, but anything better?
Oh, you're saying some kind of sparsity condition on Q? No, I don't think that we know anything particularly interesting about the sparsity of Q, except in particular situations. But, and part is a lot depends on the basis that you pick. Okay, good. So let me see, what do I want to talk about? Okay, so we talked a little bit about the case of a single polynomial. I want to try to understand if P is not negative, and this is great. But quite often we're interested in more complicated situations where we don't have a single polynomial, but we actually have perhaps some kind of set defined by polynomial equations and inequalities. And my starting point is really going to be the following. Imagine that somebody comes along and gives me a set of polynomial inequalities. And I'm trying to look for solutions over the real numbers. I'm trying to decide whether these solutions are infeasible or not. Or actually, I'm not even trying to decide. Let's imagine that for in whatever reason I convince myself that this, or I happen to know that these equations are infeasible. Right? So these equations have no solution. There's no solution of these equations over the real numbers. And my task is somehow to try to convince somebody else that that is the case. It's the co-NP version, if you want, right? In here, I'm trying to prove that there's no solutions of these equations whatsoever, right? So, natural question that again people have looked all the way in the 60s, in real algebraic geometry in particular, is how do you certify this, right? What kind of certificates are we going to use to show that this set of equations, they don't have solutions? And I mean, there's a beautiful answer to this, essentially the real version of the Nurstern sets. And I'll try to explain what this is. But in particular, what I want to, I want to try to explain, if you want, the motivation of it and why it's such a beautiful and such a somehow in retrospect obvious solution to what kind of things we want to do. Right. So also, because I want to emphasize one of the several lessons that come from thinking about this in a more algebraic geometric way, and I think these are useful for some other kind of problems. So the first one, the first, perhaps like I was telling Ben, nugget of truth that I want to highlight is kind of the following: that when you think about a set described by equations, or even if you want, think about the optimization problem. Perhaps I want to optimize some polynomial subject to these constraints, right? Which is kind of the epsilon more complicated version of this. Then quite often we think that the constraints are important. And by the constraints being important, I mean that the explicit form of the constraints are important, the way that they're presented, right? And the point, one of the lessons, if you want, of this more algebraic way of thinking about this, is that really the constraints are kind of irrelevant. The constraints are generators for an object. And somehow what really matters is another object over there. And I'll try to be very precise about what I mean by this, right? And what do I mean by this? I mean the following. Let's imagine that somebody gave me an optimization problem like this and wrote some specific set of constraints, f sub I and g sub i's. And they may have the reasons to choose some constraints, f sub I, and some specific constraints, f sub I and g sub I. But the point is, if I want, I can look at these constraints and I can start generating more constraints which are also going to be valid. Right? If you're like so let me perhaps be concrete about it, and then I'll philosophize a little bit more. So what do I mean by this? Imagine again that somebody hand me this problem and wrote f1 of x equal to 0, f2 of x equal to 0. Then I could add, if I want, like some other constraint in there that says 3f2 is equal to 0. I could. That's a valid constraint. Or I could write f1 of x plus 5 f2 of x equal to 0, and this would certainly be another valid constraint. Right? If I have any solution that satisfies this, it will certainly satisfy these other conditions over there. And furthermore, if I feel even braver, I can say, hey, why are you multiplying with constants? I can multiply in here by some arbitrary polynomial h1 of x. I can multiply in here by some arbitrary polynomial h2 of x, and write this constraint, which is also going to be valid. And by valid, I mean that this is certainly going to vanish at the feasible set. Right? So now imagine that I don't do this, but actually write all the possible constraints that I can possibly imagine. Right? I actually close, if you want, my set under the operations of taking a constraint and multiplying it by an arbitrary polynomial and taking linear combinations. Right? Which I can do, and this will generate many, many, many polynomials, infinitely many. And they're all going to vanish in the feasible set. Right? Is that clear? And there's no reason, really, why when somebody writes this, these are important. These are not the important object. Take your constraints and throw them away. I mean, it's just exactly the same way that somebody describes a subspace and gives you a basis. then who cares about that basis? We care about the subspace. Right? Of course, I'm lying. Sometimes you actually want to think about the basis, particularly if you do numerically, but not today. Right? That's only if you ever touch a computer. I think most of you are pretty safe in that regard. So, okay, good. So what is a right object in here? When you think about the most general thing that you can do, somehow it's this, really. Taking your constraints, multiplying them by polynomials, and adding them up. Like, okay, one, of course, it has a beautiful name. This is exactly the ideal. If you've ever seen this, that's great. If not, I literally mean this, which is the ideal generated by my constraints f1 to fm, let me call them. And that means exactly all the things that I can write as polynomial linear combinations of my constraints. Right? Beautiful object. We understand everything that there is to know about ideals. This is about equations. Inequality is a little bit more subtle. That's sort of new stuff, or again, new if we were in 1960, kind of is, which is really about playing the same game, but now with inequalities. Right, so I have inequality constraints, g sub I of x greater or equal than 0, and I want to play the same game. I'm a very sophisticated person. I don't want to think about the constraints g sub I that you give me. I want to think what thing do they generate. And what are the rules? What can I do if somebody gives me some valid set of inequalities g sub I and start generating more and more valid inequalities g sub I that will satisfy the same problem? It's kind of similar, but I have to be a little careful, right? Because I have to preserve the inequality. Certainly what I can do is I take sums, right? If g1 and g2 are constraints, let me forget actually let me write the dependence on x. Then g1 plus g2 is also a valid constraint, right? Same as before. Now, I can also multiply constraints. If I know that g1 is greater or equal than 0 on the feasible set, and I know that g2 is greater or equal than 0 on the feasible set, I can multiply them, and I'll get a valid constraint g1 times g2, which is also going to be a valid constraint. I cannot do the same thing that I was doing in here of multiplying with an arbitrary polynomial, because that may change a sign. But I can certainly take any, so let me write in here product. And I can write in here multiply by squares. I can take any constraint g sub I of x, and I can multiply it by an arbitrary square h squared. Right? And my claim is, of course, if g sub I is positive on the feasible set, this is going to be also non-negative on the feasible set. This is also going to be non-negative on the feasible set. What can I do? I can take my constraints and generate. I run this machinery forever until it produces a big bag of polynomials, some infinite bag of polynomials. This has a name. It has two names, actually. One is either the cone generated by the g sub i's. If you're French, you call this a pre-prime, the pre-order generated by the g sub i's. But let me be very explicit about kind of what form this takes. If you really think about taking g sub i's and somehow doing this operation, you'll see that a generic polynomial in here, the general form of a polynomial, if in here was something of this form, in here it's a little bit more complicated, so it will look something like this. It will look essentially like a sum of squares plus some sum of squares times g sub I plus some sum of squares times g sub I, g sub j. I should be a little bit more precise. That's fine. Right now, plus sum of I, j, k of x, triple products of my constraints. Right now, plus whatever. And this is a finite sum because I only have finitely many constraints. So at some point, this is going to end like sum of squares times the product of all my constraints. It's clear, or should be clear, that I only need square-free products in here, because if at any point you multiply y constraint by itself, you can just put it in here with. So all my S sub alphas are sums of squares, or polynomials which are sums of squares. So again, let me make sure that you understand what I'm doing. I'm saying, what is a set of all possible constraints that one could possibly write? And by all possible constraints, I mean all the constraints that are easy to write. There may be constraints that are true, but I could not generate it in some kind of concise way. Right, but kind of this, certainly everything that writing in here is trivially non-negative on the feasible set. Right, because each single term in here, either it's non-negative by construction, this is sum of squares, or it's a product of things that are non-negative. Yeah.
I guess you chose only squares, not mathematically, but it's easy to verify.
Yes, exactly. So everything that I'm saying would be true if in here I multiply by a positive polynomial, but I don't want to multiply by a positive polynomial, so I have no way of certifying that that would be the case. Right, but if I actually write something like this, and I write an expression of this type, I can convince you or anybody else that this is actually a positive polynomial on a non-negative polynomial on my set. Right? So really, when you talk about inequality constraints, this, or let me write in there, I will not make a choice, is really the object that you should think about. The specific set of constraints that somebody wrote is an accident. It's an accident of evolution that they decided to write those constraints when they could have written something different. And exactly the same thing is true like in this case. And by the way, none of this should come to a surprise to you, because if you've ever seen linear programming, that's exactly the same story. In linear programming, what we write, when you write Lagrange multipliers times your constraints, the only difference is that you don't allow those to be a function of x. You allow them to be constants, right? Arbitrary constants, but the whole idea is that you're trying to produce something that vanishes on the feasible set always. And in here, you don't look at this part because we're afraid of nonlinear stuff. And we only write in here constants times my constraints. But somehow this philosophy, if you want, is absolutely compatible with what you do in the linear case. And if I had more time, I could just outline why everything fits together very nicely. Right? Questions? Is this clear? Good. So why do I? Let me again. I'm in the philosophizing mood today. So let me just say one more thing. That this also highlights one other thing that may not be too important for what we're going to do today, but it's a brilliant idea. Again, not mine. It says that really, if you want to try to understand this set, and this is really one of the lessons of algebraic geometry, if you really want to understand this set, like in here, I really want to understand the feasible set of this optimization problem. What I really want to understand is the set of functions on that set. This actually tells you essentially everything that you need to know about your set. And this is very much a situation. I'm really trying to understand what the feasible set of these equations is, or if it's empty. And what I'm trying to understand in here is what the set of all functions on that set.
Is there a notion of a radical set here? Just like
yes, there's a real radical. Yeah, but I'm not talking about this today. Yeah. There is a notion of a real radical. And, yeah. Good. So why do I introduce this? Because remember what I told you. What is my problem? I have these equations. These equations are infeasible. And I'm trying to convince Ben that my equations are actually infeasible. And he said he doesn't trust me. I don't know why. But kind of what he wants is some certificate that these equations are actually infeasible. So what certificate should I hand him? And it turns out this beautiful result called the real notional set tells me that there's a very, very natural class of certificates for proving infeasibility of this. And it's a kind of thing that I think, let me write it down, and we'll all agree that kind of somehow it's the most natural thing that one can possibly do. Because it is. Because what are we going to do? Remember, what was my motivation in here? I try to write all the valid inequalities that are true on my set, all the valid equations that are true on my set, and all the valid inequalities that are true in my set. So this theorem, one direction of which is absolutely trivial, and you'll see, is really that if I succeed in finding two polynomials, f and g, in such a way that the sum of these two polynomials is a polynomial minus 1, where f in here is in the ideal, and g let me be more explicit. I want really the ideal of the equations of the f sub I, and I want G to be in the cone generated by the G sub I. And these two polynomials, f and g, satisfy the equation f plus g equal to -1. And this is really, let me write this. It really means that this polynomial is identically -1. Then my claim is that this is true. My set has to be empty. That this is infeasible. And of course, this is a triviality. It's an absolute triviality that if I succeeded in finding f and g with these properties, Ben should be completely convinced that my set is empty. And why do I say it's a triviality? Because, sorry?
Fake news.
Fake news? Exactly, because otherwise, if you could take any candidate solution in here, imagine that you don't believe me, you think that this is actually feasible, you could take that x, you would plug it in here, and you will get a contradiction. Right, because this tells me that f has to vanish on the feasible set. This tells me that g has to be non-negative on the feasible set. So by plugging in that candidate value of x, that says that 0 is equal to -1. And as far as I know, that's not true.
Pablo, here, do you want to think of the g including the constant polynomial 1?
G? No, I don't need it.
So you can add an arbitrary square to g if you want?
Yes. Yep. Yeah, that's in here, right? Yes.
Okay.
Yeah. Yeah, exactly. Good. Right? So we all agree that if I succeed in finding such an f and such a g, and I call Ben and I tell them this f and g, that's actually an absolutely valid certificate that these equations are infeasible. The non-trivial part of the theorem is that the converse is true. Any time that you have some arbitrary system of equations and inequalities, and this is infeasible over the real numbers, then there's going to be some f and some g in here for which this equation is going to be true. And I will not talk too much about the proof of the very general case. I'll just mention that, again, in the combinatorial case that many of you care about, this is also a triviality in the combinatorial case. Because essentially, this can simulate explicit enumeration. You can just check whether, at all the points of the hypercube, those inequalities hold, and then you just encode that with a polynomial. So, the existence of such a thing in the combinatorial case is, again, a triviality. So, combinatorial people, in that situation, you're happy because both directions are equally trivial. What's the non-trivial part, of course, that I don't want any polynomial f and g. I want f and g of low degree, right? Or perhaps not low degree. I want them to be compact in some way. I want to have compact descriptions of them. And that's a difficult part. Right? We'll see a lot of, particularly in Ankur's talk, work in terms of trying to understand conditions, perhaps under which certificates, let's say of low degree, exist. But if you want the general picture, is that really, as long as I'm interested in certifying equations or inequalities of this form, there's a very, very natural class of certificates that just come from really thinking this way. Good. Questions? Comments? Yes.
So if you use Tarski's procedure, you would get a test set. I mean, that would be a different proof in some sense.
Yes. So one of the ways in which historically this was proven first was essentially by what's called unwinding Tarski-Seidenberg. So you can simulate, again, Tarski-Seidenberg using polynomials, and and you can encode it this way. In fact, for instance, one of the things I will not talk too much about, when people try to probe bounds on this, on the degree of these ones, some of the bounds come from doing explicitly this, from tracing, from Tarski-Seidenberg or other decision procedure, of how do you bound the degree of these things. Yep.
Yeah. So if you were to apply this to the Motzkin polynomial,
yep.
So this is saying if I were to ask whether the Motzkin polynomial is less than or equal to minus epsilon, you'd be able to do it. But
Motzkin is trivial. You can even, the point is for Motzkin, when you multiply it by this is already a sum of squares. So Motzkin itself is not a sum of squares. If you multiply it by this, then you'll already get that it's a sum of squares. And these kind of things can be simulated by this. Yes. So if you didn't like or if you didn't know the arithmetic geometric inequality, I can just give you this explicit expression and it would be fine. In fact, maybe I should have done that. Good. So, okay, let me risk it. I just wanted to, let me just say, and I'll, just because I think, again, for general culture reasons, like, kind of, it's very natural to think about this, like, kind of at the same level that we think about linear programming duality, or at the same level that we think about the complex null-Stellen sets. Right? Because really, like, when you think about equations or equations and inequalities, there's like 4 natural cases, depending on whether you look at equations over an algebraically closed field, like the complex numbers, or an equations over a formally real field, like the real numbers, and whether you look at linear equations or you look at polynomial equations. And somehow there's very natural classes of certificates for all of these cases, and somehow they're related in very natural ways. Right? If you look at linear equations over a field, then kind of you're solving AX equals to B or trying to prove the infeasibility of this. And kind of what you're really looking is at kernel range type problems. So if you have a system of linear equations that it's infeasible, you can find a linear combination of the equations that it's equal to 1. Right? I mean, that's for the case of linear equations over the reals, that's exactly LP and Farkas lemma. For the case of complex equations, complex polynomial equations, the certificates that we use to ensure that a variety is empty, that a set of polynomial equations doesn't have solutions, that's exactly the null-Stellen sets. And again, I don't have time to describe it, but Jesus would be a great person to tell you everything about this, even in the combinatorial case. And for the complex case, for the real case for polynomial equations, that's exactly what we talked about, the real null-Stellen sets. And I guess the other thing that I should mention is that all of these ones, they have kind of associated computational tools. Right? This is, of course, just linear algebra. If I want to decide or to prove certificate of infeasibility about linear equations over any field, you do linear algebra. If you want to think about linear equations, linear inequalities over the reals, and you do LP, and you would do simplex or interior point methods or whatever. If you look at polynomial equations over the complex numbers, essentially you're trying to find solutions of this equation where you're writing here 1 rather than 0, finding a solution to the null-Stellen sets. So one way of doing this, closer to what we're going to do in here, if you were to put a bound on the degree of the H sub i's, then this is just solving a linear algebra problem. If you don't want to solve a linear algebra problem, you can do Grosvenor basis or something like this. So or you could compute Grosvenor basis using linear algebra. So those kind of nice computational techniques associated to finding certificates of infeasibility for linear equations. And of course, I guess the reason why I'm talking about this is because if I want to, again, not just take this as a given, but if I actually want to find f and g's, I have to find kind of sums of squares in here and polynomials h sub I in here in such a way that this equation will be satisfied. And when you think about what is involved in it, it's really just a semi-definite problem, right? Because what do we have to do? We have to, this depends affinely. This is a linear condition between the s sub i's, all these different s sub i's, and the only conditions that I have is that all these polynomials, they will have to be sums of squares. So somehow, even though I don't write it explicitly, and nobody should ever write the things explicitly, the point is once you restrict the degree, in here I claim that kind of the degree of this is less than or equal than something, let me call L, the level of the hierarchy. My claim is that this is just a semi-definite problem. Right? Again, we don't need to write it explicitly, but the point is I'm really finding certificates in here of low degree. And by going up in the degree, I know that kind of eventually solutions will exist by these real null-Stellen sets. Right? Good. So somehow this picture, I find it very useful. It really allows you to think even in other situations. The first thing that you should really think about is, okay, how do you even certify that solutions don't exist? And of course, there's a lot of connections when you think about what you were doing in here with proof systems, right? I know what's I know. Yeah, Jacob. Yeah, sorry. He's an expert on this. On the aspect of really interpreting these kind of things exactly as a proof system, right? You start with the basic set of axioms in here, and what am I doing? I'm just deriving more and more things that are consequences of the set of axioms that I wrote. And all these things are the things that are conceivable, concisely provable, from my G sub i's. Right? And the same thing is true for the ideal. The restriction in there on the degree essentially says that these are the things that I can show. Yeah,
Pablo?
Yes.
So can you derive the solution to Hilbert's 17th problem from this? Or is
yes. Yeah. So that's, again, it follows. Let me not do it because I don't have time, but essentially if you want to show that, let me tell you the basic version, but if you want to show that a polynomial is, remember, the 17th question is if P is non-negative, is it the sum of squares of rational functions? So the version that I wrote is I want to know whether this is empty, right, or my equations is infeasible. So that's the same thing as saying that x such that P of x is negative, that this set is empty, right? So this set is empty. In here I have strict inequalities. Strict inequalities is not quite of the form of the theorem that I wrote in here. By the way, there's a more general version of this where you allow for inequations or strict inequalities. Let me not do this. So how do you deal with this old algebraic geometry trick? You introduce a new variable, and you write this exactly as the equation 1 minus this is 0, and P less than or equal than 0. Where y is a new variable. Right? These equations are infeasible, so P cannot be 0 because of this equation, so P has to be strictly negative. Right. And if you just apply the real Nullstellensatz to this, and you play around, you get exactly a representation of the sum of rational functions. So of course, historically, it's an awful thing to do. This only came much later, and much of the motivation was exactly this. But yeah, it's an absolute special case of this very general stuff. And by the way, lots and lots and lots of things are special cases of this. This is, in a sense, the most general thing that one can, again, one has to be a little bit careful about what does it mean, but really it's hard to understand how to generate more and more things that don't come from constructions like this.
This can be used to justify why you don't necessarily need positive polynomials there, maybe, right? Because
yes. Well, the thing is, somehow it's cheating, right? If I had access to non-negative polynomials, then I think you can essentially do this in one shot, right? Because yeah. But you're absolutely right? What the theorem tells you is that you can give a constructive, easily verifiable certificate. I don't need to rely on the promise that you tell me that some polynomial is non-negative, right? I can verify it myself. Good. Questions? So, and really this is a point that I want to be very, very clear. Somehow once you look at this equation and you understand that this is a way of certifying the emptiness or the infeasibility of equations, the only thing that you do is you say, okay, now I want certificates of low degree. And you bound those degree, or you stratify if you want the set of proofs in whatever way you want. If you don't like degree, then you can pick in sparsity or whatever notion of stratification of a set that if you want some way of having these contains in each other, that will give you a different hierarchy. Different ways of doing things. And there are lots of games that one can play. So let me just at least mention also, again for general culture, like a different variations or even special cases that somehow one looks all the time, because when you start assuming more and more, or you assume perhaps different properties about your f sub i's and g sub i's, then perhaps you can simplify or change, if you want, the structure of things in here. So let me talk about perhaps rather than non-negativity, rather than emptiness. Let me talk about the question of trying to certify that P is positive on some set. right? And again, let me just pick the inequalities. I don't care about the equations for what I want to write. I just want to contrast or compare a few things that one can possibly do. So in algebraic geometry, there's different kinds of, or real algebraic geometry, there's different kinds of certificates that one can think about, again, depending on what you're willing to assume on the G sub i's. So one notion is kind of like, this full, if you want, which is really, again, I think it's the most general thing that one could possibly do. But then, for instance, people have looked at particular cases. Like Handelman, for instance, look at representations. And again, I may miss some of the assumptions and whatever. Or for instance, you look at your polynomials being linear. So essentially, this corresponds to the case of a polynomial non-negative on a polytope, right? And in that case, one can give what's called representation theorems. Let me write perhaps a general form in here. All the theorems are of the form, if you have a polynomial, actually, and for all of those, you need strict positivity on that set for exactly the same reasons that we talked about before. If you insist on inequalities, then you will not have certificates of this type, although those kind of things will work. Sorry, these kind of things will work. Well, for instance, you may want to represent P in some particular form. Let me make it precise. So for instance, in the particular case where these Handelman representations are whenever my constraints are linear, so really it's a polynomial strictly positive on a polytope. So what Handelman says that in that case P has a representation of the form, let me actually perhaps write it explicitly, that where all the S sub i's are constants. So whenever you look at positivity of a polynomial, strict positivity of a polynomial on a polytope, then it's enough to pick all the S sub i's to be constant. So this gives some linear programming hierarchy. Right, kind of Schmutgen has some other kind of results where, for instance, what you require.
Pablo,
yes.
Does that have cross terms too, or no? So
yes, with cross terms.
Okay, so
yeah. So the only thing.
Requires using cross terms.
P is not convex, right? My polynomial is not convex.
No, exactly. So I'm saying you still need the.
You still need the products, but you don't have kind of in that case. And again, there's typically some. Maybe let me be a little bit more precise in here. Plus compactness. So Schmutgen has another beautiful theorem that says what happens in the, let me call this set S, when S is compact. And in that case, you don't need the product. Schmutgen is, no, Schmutgen says that in the compact case, then this is fine. Kind of strict positivity is kind of enough for a representation of this type. So it says that P itself will have a representation of this type. Kind of then Putiner has another version, which is essentially the one that was used by Lasserre, that says that if S is, let me write algebraically compact, which it means, and this is very interesting, so it means not only that it's compact, but I need to have some algebraic way of checking that the set is compact. Right? So what that means is that not only if you can come with your set and tell me my set is compact, but you have to provide an algebraic certificate of compactness. So for instance, by showing that there's some linear combination of your equations or a polynomial linear combination of the equations that that gives you a unit ball or something like this. In which case, what happens is that you don't need the products. So you don't need the products of the constraints. So what's good about these kind of things? The more structure you put on these ones, kind of the different, there's different ways in which you can play your set. One thing that again we have to be careful with this kind of results is that none of these results they tell you anything about trade-offs in terms of the degree. It may happen that okay, you don't need the products, but now you need much higher degrees in your certificate. In fact, that is known. I mean, Schmutgen has a paper kind of showing exactly that these representations without products can be worse, at least in certain cases. So somehow there's general trade-offs between how general your certificates are versus what you assume on the degrees. But I think what's really important in here is not the form of kind of you use this or that, but really somehow what the things are doing. And the only thing that they're doing is you try to generate as many constraints as you can, and then you try to find the contradiction. And all of this can be completely automated because underneath you're just solving semi-definite problems. Yeah.
So who approved the full positive sense sets? Is that
So this version, I mean, depending on how explicit you want to do, is either Krivin or Stengel. Certainly Stengel wrote it very explicitly in exactly this form. Kind of some algebraic geometers claim that this is essentially all in Krivin's paper. Kind of, and of course, yeah. Sorry.
So what's the difference between the full P sets and the Schmutkin thing?
Oh, so in here, if you want, in here I'm talking about infeasibility. So this may require, when you apply it, in this case, you take your polynomial and multiply your polynomial by something else along the lines of what you did there. So you could show, for instance, that 1 plus the sum of squares times q times p has this form. Right, which is a more general certificate than taking this equal to 0. Right. And again, there's examples where you actually gain a lot by doing this. So there's many parameters, things like that. Okay, good. Questions before I move on? So I won't be moving on too much. So one of the things that's kind of somewhat frustrating in here is that it's not terribly easy to understand why the things are true. And again, in the general case, if you don't really know anything about your polynomials, g sub I, then the point is very complicated things can happen. Right? It's very much like, I don't know, when you look at the Nullstellen set, right? I mean, the degree bounds, for instance, sometimes are very large, and they're very large not for geometric reasons somehow, because, but they're large because polynomials can do fun. You can encode funny stuff inside the points. Think about multiplicities. You can essentially look at polynomials that, for the geometry is not apparent from the equations. But one thing that at least I want to highlight, is that it's kind of otherwise somewhat mysterious that you end up with these kind of things, is why, like I said earlier, in the hypercube case, in the particular case where you look at the polynomial on the vertex of the hypercube, why this kind of statement is trivial. Right? Why somehow it's very easy to certify that if my polynomial is indeed non-negative in the hypercube, then I can write very explicitly a sum of squares certificate that that's the case. Right? And again, it's a trivial idea, but kind of to some extent, the proof of the general case, at least in certain situations, is not much more difficult. Think about, instead of the hypercube, think about the compact situation, and certainly the same kind of thing will be true. So why is this even true? Or what am I trying to show? I'm trying to show that if P is non-negative on the hypercube, on the vertex of the hypercube, there's some nice sum of squares certificate that certifies this. And the idea is kind of very, very simple, right? So let me define, so think about the hypercube in here. So I have a function that's defined somehow in the vertices of my hypercube. In there, and let me try to understand this function first. I give a delta function. The function that's 0 everywhere, but it's 1 at a particular point. Right, so let me write it explicitly. So for instance, if this point, let me write it in the easiest form first. Let me imagine that this point, my preferred point, is a all ones vector. Right, then of course you can write it very explicitly. So what this function is 1 plus x1 divided by 2, 1 plus xn divided by 2. Right? So I claim that the delta function is exactly kind of this function, which is kind of easy. Right? If any x sub I is minus 1, then this vanishes. If all the x sub i's are equal to 1, this gives me the value 1. Right? So this, of course, only works at this point. But of course, I can do this at any other point by doing some kind of linear transformation. Or if I wrote the function explicitly, if this vertex is a vertex v, then the only thing that changes, I think I have to do something like this. v1 to vn. Simple exercise to check. This function pv of x takes a value 0 at every vertex, except at the vertex B. Is that clear? Not so clear? More or less clear? Right, the same argument that I was saying before, right? If all the V sub i's were V sub I, where V is a vertex of the hypercube, plus minus 1, whatever.
You want 1 plus V. 1 plus VI xi, right?
I want 1 plus VI. Is that true? Certainly when it's 1, it works. When it's minus,
It works either way. It's the same circle.
it changes the sign. I mean, okay, some version of this. I just want to ensure that I get a 1 in here and not a minus 1. So whatever version it is, like something like this. So why do I do this stupid thing? Because the point is, if I have the delta function, then key insight, the square of the delta function is a delta function. Let me say it in a different way. The delta function is a square. So what this tells me is that I can write any function p of x as a sum of p of y, delta y of x squared. Right? Is it clear why this is the case? Because this is the same thing. Perhaps I should have written this earlier. Now, sum of p of y. Actually, let me do it that way so you don't get super confused. Let me first claim that this is true, right? Which is clearly true because this is 0 at every point except when y is equal to x. So I get the same thing. And like I said before, the delta function, when I square it, I get the same thing. So what this gives is an explicit representation of my function as a sum of squares. And these coefficients are fine. They're not negative because my polynomial is not negative. Right? So in the discrete case, the fact that the non-negative polynomial is a sum of squares is an absolute triviality. Is this. In the compact case, it's not much more difficult. Because really the only thing that you have to do is you have to show that you can approximate the delta function with polynomials. But essentially the same thing is kind of true. And of course, implicitly, this is all the way in Polia's papers, all these papers. Somehow when you unwind what's actually going on, it's really some kind of argument of this type. That when you look at these hierarchies, what they end up doing in the limit is just evaluating the polynomial at all the possible points. And that's why when you let the degrees go to infinity, essentially you recover completeness. Again, the general case is more complicated. There's reasons why somehow the non-geometric situation is more complicated, but again.
But Pablo, most of the time when we want to use this stuff, we don't want a polynomial of degree.
That's right. No, and I'll talk about this. Of course, the same thing as in here. The whole game is, there's two aspects of it, right? The whole game is that depending on what you want to do, you never care about the converse statement. Because once you succeed in finding the solution of the SDP, well, this is proving the bound that you want. If you want to prove theorems, then of course you want to have much finer control of what the degree of these polynomials are, depending on the structure of your polynomial P.
So is there any way to gain insight from this delta function expansion? So clearly it proves your converse, which is fine. But is there any way to see from that such an expansion why there'd ever be hope? Or what we need in order to get a very low degree.
So the question is, can you actually use this somehow to produce bounds on the approximation quality? The answer is you can, by understanding how well delta functions can approximate, how well polynomials can approximate the delta function. You do get bounds. Not a problem, but a feature of that approach, if you think about what I did in here, is I didn't use any property whatsoever of P. So in that case, and you get results about approximation, for arbitrary polynomials. And the point is that those tend to be things somehow worse than all the situations like max cut or all the interesting situations where you put additional structure on the polynomial P.
Quick question on the line. So here there are 2 to the n points.
Yes.
The degree is n, but that has somehow uses a special structure of the cube, doesn't it? Because if you have 2 to the n points in the real line, and I tell you values, the degree has to be 2 to the n in general.
Yeah.
So
the point is somehow the degree is not really the right measure, or let me say it this way: on the hypercube, linear degree is really bad, right? I mean, saying in the hypercube I have a polynomial of degree n is really bad. On the line, somehow saying I have a polynomial of degree n is not bad. So I think it has more to do, not with this argument, but more to do with what is polynomial time or not polynomial time in that case.
Just really quick, I mean, just building on what you both just said, the dimension of the space of polynomials of degree 2 to the n in one variable is 2 to the n, and the dimension is what here? It's n to the n? Right?
Yeah, n choose, like the sum, essentially 2 to the n, yeah.
It's still 2.
The sum of n choose d.
Both 2 to the n.
Before 2 to the n, but you can do with degree n here, always.
But I think that what matters is the dimension of the
The dimension of the vector space, right? Even though you can do it with polynomials of degree n, where you write this semi-definite program, if you do it that way, you need to parameterize all the polynomials of degree up to, yeah, and that's essentially this exponential. Okay, good. So let me say, two things. And somehow point out. Okay, let me point out very explicitly to the kind of things that I think Ankur will talk about in much more detail, which is exactly the question of how, for particular problems, how do we control the degree of this certificate? Right? Whenever I look at either random problems or problems of a particular type, how do I get bounds on the degree of these certificates? Right? And this is a very interesting question. The other thing that I want to talk about is somehow all this sum of squares stuff is a very general machinery, right? Notice that there were no assumptions at all about what these polynomials f and g's were. So somehow, and again, some of you have seen this picture, there's like this very general machinery where somehow you start with your polynomials or polynomial constraints, you go to the SOS cloud, and in the end, what you get is some kind of big semi-definite program in there that you have to solve in some kind of way. And there's many questions, I guess, that one can ask, or many research questions, if you want, that I think that one needs to deal with. I mean, of course, one would like to have semi-definite problems that are small. One would like to have algorithms for solving this, and I haven't at all talked about algorithms for doing this. I think Ankur will mention a little bit, and of course we'll hear a little bit more, I think later when there's talks about interior point methods, for instance, for solving these semi-definite problems. But also a big part of, I think, what one needs to do and what we do is really trying to understand in here what are the best semi-definite problems that you can write. And by this I mean the following. For most problems that we care about, these polynomials are not arbitrary. There's a lot of structure in the polynomials that they come, whenever you're faced with any particular problem. And the question is to what extent you can write better semi-definite programs in order to do this. So there's techniques for doing this. And the reason why I want to mention this is because they connect to a number of things that we'll see in a more or less explicit way, I think, later. So one has to do, and I guess we've seen a little bit of this before, in the case where I have explicit equations. Right, so in my notation that I use in here is when I have equations f sub I of x equal to 0. Think about, in this case, if I work on the hypercube, I'll have these equations x sub I square of -1 equal to 0. So in that case, even when you think about the problem of deciding if a polynomial is a sum of squares or not, somehow the general machinery that I talked about in here may be somehow a little bit suboptimal. In the following sense, think about the case that I have a polynomial and I really only care about this polynomial in the hypercube. Then one of the things that I think many of you are familiar with is that really I don't want to think, if I'm interested in a polynomial in the hypercube, I can always think that P is a multilinear polynomial. Right? I can essentially, on the hypercube, the square of any monomial is going to be equal to the monomial itself. X sub I squared is equal to x sub I. Well, it depends on, let me do the 0, 1 hypercube just so it's clear. So in that case, if we look at square-free monomials, and in that case, for instance, indexing my sum of squares matrix by all the monomials of degree less than or equal than something doesn't make sense. What I really want to do is somehow index only by the multilinear monomials. And similarly, when I expand this equation and I write this is equal to this, I don't want to literally check that they're the same. I want to check that they reduce to the same thing under this multilinear map, right? That they just agree on the values of the hypercube. So what's a general version of this? So essentially, if I have equations in here, what I want to work is not on the polynomial ring, but I want to work on this quotient space. I want to mod out but the ideal. And if I have a nice way of working on this quotient ring, like if I have a Grosvenor basis or something, then that's a much nicer way of writing this kind of sum of squares type things. The other case, which again I will not talk too much, I just won't say anything, is a case of sparsity. Right, so perhaps your polynomial, your input polynomial, think about now the case of just deciding if a polynomial is sparse, then perhaps my polynomial is very sparse. Like, perhaps there's a better way of doing the sum of squares stuff, and actually there is, like, kind of if your polynomial is sparse. And one has to be a little careful about what do we mean by sparse. There's both a naive notion of sparse as having few coefficients. There's the algebraic geometric notion of being sparse. That means that the Newton polytope is small. There's something called the Newton polytope, and if that polytope is small, then that will mean that your polynomial is sparse. So this we more or less understand. Very interesting question that we don't know. Actually, hopefully some of you would be interested in this. What happens in the black box case? Right? I have perhaps a polynomial given in some kind of black box way, like perhaps gray box if you want. Perhaps there's some structure in there. Can we do any of this stuff in some kind of cleverer way? I don't know. Symmetries is kind of a very interesting situation. So symmetries is a case where you have some polynomial. Again, let me think about the case of a single polynomial p, like before. And p may be invariant under the action of a group. So perhaps there's some group of transformations, and p happens to be invariant under this group action. Simplest case, think about p being invariant under permuting all the variables. Simple case. So it turns out there's a very nice theory that one can do in this case, where you don't really need to work somehow on the doing sum of squares on the big polynomial ring, but you can work on what's called the invariant ring. And there's some very nice representation theoretic tools, somehow to understanding how do you work in this case. And there's some very interesting and recent developments. I love this stuff. Some connections between this symmetry reduction approach and something called flag algebras that Rasborov introduced a while ago. So the connections with symmetries is like this very nice paper that I like a lot by Raymond, Singh, Saunderson, and Rika Thomas, which somehow connect this idea of flag algebras with symmetry reduction. And the way that I like to describe this, these guys will kill me, is that really doing sum of squares in asymptopia. Like this idea is that if you don't want to do sum of squares with finitely many variables, like one does in here, but you actually want to work directly in the limit, where you have an infinite number of variables. And there's a very formal way, of somehow either taking this limiting process, which is what they do, or somehow what Rasborov was doing, working directly in asymptopia, and somehow there's a very nice connection between these kind of things. So the point, again, I don't expect you to get this. The point I really want to make is that there's a lot of, somehow once you take these very basic constructions and then you add structure, you say, okay, I'm not really looking at arbitrary polynomials, generic polynomials. My polynomials are very special. You start recovering lots of things that don't look at all like the standard stuff. And this is, I think, a very interesting process. I think it will be very interesting, or it is very interesting to understand what are the limits of this kind of machinery. I think Ankur will talk a lot about, again, in particular, this question of how do we get better, how do we understand, I guess, the behavior of these relaxations, either for random problems or for concrete problems. And the other thing, which I didn't mention anything at all, and he'll talk about much more explicitly, is what is a dual picture. What happens on the dual side. Every semi-definite program that you'll ever meet comes with its dual. So something that's perhaps not obvious is what is a dual picture in here. And the other thing that's very intrinsic and will connect with the kind of things that Michel was talking about is how do we take these dual solutions and round them in some way? How do we even think about this? And there's some very beautiful machinery that a whole bunch of people, including many of the audience, have been working in terms of how do we take these solutions and produce actually primary solutions from this. So I think that's it. Questions?
Questions? Got it.
somebody else wants to go.
Yeah, if you expand the set of coefficients from squares and add like all these inequalities that you get from arithmetic geometry, so then you don't get led to STPs. To what? Do you get to something computationally tractable?
I mean, so certainly you can add. So let me talk about the general picture in a second. You can certainly add any valid inequalities. So if, for whatever reason, I happen to know that, there's some family of polynomials which are non-negative, like, Motzkin, I can very easily throw in there plus coefficients times Motzkin.
You throw in all ones
So that's the thing. I don't know any. I mean, I think, for instance, what one does in all this, sum of non-negative circuits polynomials, or you essentially pick a sparsity pattern. And you only play with the coefficients. So essentially, you pick certain coefficients, essentially a simplex in the Newton polytope is a simplex. Then you pick an additional point, and then you write geometric programs that will describe inequalities between these n plus 1 coefficients, and somehow you throw this in. It would be very, very nice if there was a way of somehow spinning this under the natural group action, right? I think it's not just about adding. Think about in the case of Motzkin, right? I don't want to add Motzkin in 3 variables. I want to add all the Motzkins that result from plugging in, any possible values of x and y. Think about, I guess in axioms terms, I want to add the template. I don't want to add, the axiom. And as far as I know, we don't know how to do this.
Is there any complexity advantage of the certificate over the decision procedure?
I think the miracle in here, if you want, is that not only the certificates exist, but somehow we can actually find them efficiently by solving these semi-definite programs. Yeah, somehow there doesn't seem to be any advantage in this case, and let me perhaps also be just a little bit precise. I don't want. When I claim that we write this equal to -1, and I make all these statements about the degree of the f sub i's, which is true, right? I mean, every time that I talk about the degree of these polynomials, I really mean the syntactic degree, right? So I'm not taking, because for instance, the degree of this polynomial is actually 0, right? The degree of this whole thing, this is exactly equal to the polynomial -1. So the true degree is 0. There's lots of cancellations that happen. So I'm really, when I talk about degree, I mean the syntactic degree. The degree that you would obtain if you just look at this expression, you ignore the fact that cancellations may happen. Yeah, so.
Yeah, for the general certificate, is there a degree bound that depends only on the number of variables and, well, I guess the degree of the defining equations?
There are, in the fully general case, if you don't put any assumptions whatsoever, they're awful. And by awful, I mean, yeah, like they're super exponential, whatever. Yeah. None of that happens in the concrete case where somehow there is a set and you have access to that set. But it's very different from the situation where I just hand you some equations. You have no idea whether this is feasible or not. You have no idea how the infeasibility of this is encoded. The same thing that happens in the Nurstellen sets, that you can write these telescopic equations, where you don't know. I mean, there's funny games that one can play with polynomials. Let me say that this way. So the bounds are actually pretty bad. I mean, the known bounds in the degree that in the fully general situation, they're pretty bad. None of this happens, like in this kind of concrete situations where you have a set, and and you have access, and you know that somehow that set has an interior, and it's not a mysterious thing. I can be more precise offline, but the point is that if you just see equations, it's very difficult to reason about whether these equations are they define a set or they don't.
Last questions. All right, let's thank Pablo.